Hello and welcome. In this video, we'll be diving into the world of logarithms, a fundamental topic in IB, DA-HL mathematics. By the end of this session, you'll be able to manipulate logarithmic expressions using key properties, solve exponential equations, understand and graph logarithmic functions, and apply these concepts to real-world problems like growth and decay. Let's get started. Our first objective is to manipulate logarithmic expressions. To do this, we need to be very familiar with the three main laws of logarithms. First, the product law states that the logarithm of a product is the sum of the logarithms. Second, the quotient law says the logarithm of a quotient is the difference of the logarithms. And third, the power law allows us to bring an exponent down as a multiplier. Let's see these in action with a few examples. Consider the expression 4 times the natural log of 2 plus 2 times the natural log of 3. First, we'll use the power law to move the coefficients back into the logarithms as exponents. This gives us the natural log of 2 to the power of 4 plus the natural log of 3 to the power of 2. Now we can simplify the exponents. 2 to the 4th is 16, and 3 squared is 9. So we have the natural log of 16 plus the natural log of 9. Finally, we use the product law to combine these into a single logarithm. The sum of the logs becomes the log of the product. 16 times 9 is 144. So the simplified expression is the natural log of 144. Let's try another one, this time with subtraction. Simplify 1/2 times the natural log of 9 minus the natural log of 2. Again, we start with the power law. 1/2 times the natural log of 9 becomes the natural log of 9 to the power of 1/2, which is the square root of 9. The square root of 9 is 3. So we have the natural log of 3 minus the natural log of 2. Now we apply the quotient law. The difference of the logs becomes the log of the quotient. So the final answer is the natural log of 3 over 2. These examples show how to combine multiple logarithms into one. Now let's go the other way and expand a single logarithm. Expand the natural log of the square root of e. First, let's rewrite the expression inside the logarithm using exponent rules. The square root of e is e to the power of 1/2. So we have e times e to the 1/2. When multiplying powers with the same base, we add the exponents. 1 plus 1/2 is 3/2. So the expression is the natural log of e to the 3/2. Now we can use the power law to bring the exponent to the front. This gives us 3/2 times the natural log of e. Remember that the natural log, ln, is the logarithm with base east, so ln e is 1. Therefore, the final answer is 3/2. We have now seen how to use the laws of logarithms to simplify and expand expressions. This skill is crucial for solving logarithmic and exponential equations, which we'll cover next. Our second objective is to solve exponential equations. We'll focus on cases where the bases cannot be easily made the same, requiring the use of logarithms. The key strategy is to take the logarithm of both sides of the equation. This allows us to use the power law to bring the variable exponent down, turning the equation into a linear one that we can solve. Let's start with a classic example. Solve for x in the equation 2 to the power of x equals 30. We can't easily write 30 as a power of 2, so we'll take the logarithm of both sides. We can use any base, but base 10 or base e are common because they are on most calculators. Let's use base 10. We take the log of 2 to the x and the log of 30. Now apply the power law on the left side. The exponent x comes down as a multiplier, so we have x times log 2 equals log 30. Finally, we isolate x by dividing both sides by log 2. This gives us the exact solution. X equals log 30 divided by log 2. Using a calculator, this is approximately 4.91. Let's try another one, this time involving the natural logarithm. Solve for x in the equation 3 times e to the power of x over 2 equals 21. First, we need to isolate the exponential term. We can do this by dividing both sides by 3. 21 divided by 3 is 7. So the equation becomes e to the power of x over 2 equals 7. Since the base is e, it's natural to take the natural logarithm of both sides. We take the natural log of e to the x over 2 and the natural log of 7. On the left side, the natural log and the exponential function with base e are inverses, so they cancel each other out. This leaves us with just the exponent, x over 2, on the left side. So x over 2 equals the natural log of 7. To find x, we multiply both sides by 2. The exact solution is x equals 2 times the natural log of 7. This is approximately 3.89. Now for a more complex type of exponential equation, one that can be solved by factoring. Solve for x in the equation e to the power of 2x minus 5 times e to the power of x plus 6 equals 0. Notice that e to the 2x can be written as e to the x squared. This equation has the form of a quadratic. Let's make a substitution to see this more clearly. Let u equal e to the x. Then the equation becomes u squared minus 5u plus 6 equals 0. This quadratic equation can be factored. It factors into u minus 2 times u minus 3 equals 0. This gives us two possible solutions for u. U equals 2 or u equals 3. But we're solving for x, not u, so we need to substitute back. Since u equals e to the x, we have two separate equations to solve. E to the x equals 2 and e to the x equals 3. Taking the natural log of both sides for each equation gives us our exact solutions. For the first equation, x equals the natural log of 2. For the second, x equals the natural log of 3. These are the two exact solutions to the original equation. We have now successfully solved various types of exponential equations using logarithms. This is a powerful technique for finding exact solutions. Our third objective is to understand and graph logarithmic functions. We'll start by looking at the relationship between exponential and logarithmic functions. Remember that a logarithmic function is the inverse of an exponential function. This means their graphs are reflections of each other across the line y equals x. Let's consider the general exponential function f of x equals a to the x, where a is greater than 1. This function has a domain of all real numbers, a range of all positive numbers, and a horizontal asymptote at y equals 0. It always passes through the point 0, 1. Now let's find its inverse, which is the logarithmic function. The inverse function, f inverse of x, is log base a of x. Because it's an inverse, its properties are swapped. The domain is now x greater than 0. The range is all real numbers, and the asymptote is now vertical at x equals 0. It passes through the point 1, 0. Here you can see the graphs of y equals 2 to the x and y equals log base 2 of x. Notice how they are perfect reflections across the line y equals x. The horizontal asymptote of the exponential function becomes the vertical asymptote of the logarithmic function. Now let's analyze a transformed logarithmic function. Consider the function f of x equals log base 2 of x minus 1 plus 1. First, let's find the domain. The argument of a logarithm must be positive. So x minus 1 must be greater than 0, which means x must be greater than 1. The domain is all real numbers greater than 1. The vertical asymptote is where the argument is 0. So the vertical asymptote is the line x equals 1. Next, let's find the x-intercept by setting y equal to 0. We set the function equal to 0 and solve for x. Subtracting 1 gives log base 2 of x minus 1 equals negative 1. Converting to exponential form, x minus 1 equals 2 to the power of negative 1, which is 1/2. Adding 1 to both sides gives x equals 1.5. So the x-intercept is 1.5, 0. There is no y-intercept because the domain x greater than 1 means the graph never touches the y-axis. Here's the graph. You can see the vertical asymptote at x equals 1 and the x-intercept at 1.5. The graph is the basic log base 2 of x graph shifted 1 unit to the right and 1 unit up. Finally, let's find the inverse function, f inverse of x. We start with y equals the function. To find the inverse, we swap x and y. So x equals log base 2 of y minus 1 plus 1. Now we solve for y. Subtract 1 from both sides. Convert to exponential form. Y minus 1 equals 2 to the power of x minus 1. Add 1 to both sides. So the inverse function is f inverse of x equals 2 to the power of x minus 1 plus 1. This is an exponential function. As expected, its horizontal asymptote is y equals 1, which is the vertical asymptote of the original function. Its domain is all real numbers, and its range is y greater than 1, which is the domain of the original function. We have now explored the properties and graphs of logarithmic functions and how they relate to their exponential inverses. Our final objective is to apply logarithms to real-world problems, specifically in the context of growth and decay. Many natural phenomena, like population growth, radioactive decay, and compound interest, can be modeled by exponential functions. Logarithms are the tool we use to solve for the exponent, which often represents time. Let's look at a population growth example. A farmer observes an insect plague. The affected area, A sub n, in hectares, is given by the formula 1000 times 2 to the power of 0.7 n, where n is the number of weeks. We want to find the time it takes for the area to reach 5,000 hectares. We set up the equation by substituting 5,000 for A sub n. This gives us 5,000 equals 1,000 times 2 to the 0.7 n. First, isolate the exponential term by dividing by 1,000. 5,000 divided by 1,000 is 5. So 5 equals 2 to the 0.7 n. Now, take the logarithm of both sides. Let's use base 10. We have log 5 equals log of 2 to the 0.7 n. Apply the power law on the right side. The exponent comes down, so log 5 equals 0.7 n times log 2. Finally, solve for n. Divide both sides by 0.7 times log 2. This gives n equals log 5 divided by 0.7 times log 2. Calculating this gives approximately 3.32 weeks. So it takes about 3 weeks and 2 days for the area to reach 5,000 hectares. Let's try a financial growth problem. Irina invests 5,000 euros at 5.2% interest compounded annually. We want to find how long it takes for her investment to reach 20,000 euros. We use the compound interest formula. The formula is A equals P times 1 plus R to the power of T. Substituting our values, we get 20,000 equals 5,000 times 1 plus 0.052 to the power of T. Simplify the expression inside the parentheses and divide by 5,000. 1 plus 0.052 is 1.052. 20,000 divided by 5,000 is 4. So 4 equals 1.052 to the power of T. Now, take the logarithm of both sides. Let's use base 10 again. We have log 4 equals log of 1.052 to the power of T. Apply the power law. This gives log 4 equals T times log 1.052. Solve for T. Divide by log 1.052. T equals log 4 divided by log 1.052. This is approximately 27.3 years. Since interest is compounded annually, we must round up to the next whole year. So it will take about 28 years for the investment to reach 20,000 euros. We have now seen how logarithms are essential for solving real-world problems involving exponential growth and decay. This concludes our objectives for today. Let's quickly recap what we've covered. We started by mastering the laws of logarithms, which are the foundation for all logarithmic manipulation. We then use these laws to solve various exponential equations, including those that could be factored like quadratics. We also explored the properties and graphs of logarithmic functions, understanding their relationship as inverses of exponential functions. Finally, we applied these powerful tools to solve practical problems in growth and decay. To solidify your understanding, here are 5 practice questions. Pause the video, work through them, and then check your answers. Here are the questions. Question 1 asks you to simplify a logarithmic expression. Question 2 is a standard exponential equation. Question 3 involves a quadratic-like exponential equation. Question 4 asks you to find the inverse of a logarithmic function. And question 5 is a compound interest problem. Welcome back. Let's go through the answers. For question 1, using the power and quotient laws, we get the natural log of x squared y over z cubed. For question 2, taking the log of both sides gives x equals log 120 divided by 2 log 5. For question 3, factoring gives e to the x equals 2 or e to the x equals 5, so x equals ln 2 or x equals ln 5. For question 4, the inverse is f inverse of x equals 3 to the power of x plus 1 minus 2. And for question 5, the annual interest rate is approximately 9.86%. I hope this video has helped you build a strong foundation in logarithms. Keep practicing, and you'll master this topic in no time. Thank you for watching.